Electric potential energy. Start with two charges initially at rest, with plus big Q at the origin and plus little q at infinity. Takes a little imagination for that. In order for the little q to move towards plus q, the big one, a force opposite to the Coulomb repulsive force needs to be applied, since like charges repel. So here's the force of the electric field, right? It's a repulsive force, tries to move little q away. So we need an opposite force, and we're going to call that external force, to push it in this direction. Note that this force is constantly increasing as little q gets closer to big Q, since it depends on the inverse of the square of the distance between the charges, 1 over r squared. And as r decreases, as this q gets closer and closer, r will decrease, so the force will increase. Right? The force is kqq over r squared. We can take advantage, again, of the similarities between gravitational force and field and electric force and field. The work done by each force does not depend on path, as they are conservative forces. This allows us to relate work and potential energy as we did in the energy unit. Since the work that a field force does, and in this case it'll be the electric force, is equal to the negative change in potential energy, we also know that the work that the external force is opposite and equal to the work that the electric field force does. So here's the electric field trying to push the charge away, and here's the external force pushing it in this direction. So we combine those two equations and we find that the work done by the external force will equal the change in potential energy. Since the potential energy depends on the electric force, we will call it electric potential energy. The electric potential energy increases when the external force does positive work on a moving charge. So here's positive work by an external force trying to push these two charges together. The electric potential energy decreases when the external force does negative work on a moving charge. The actual calculation of electric potential energy will be done later in AP Physics C, but it results in this equation for the potential energy due to two-point charges separated by a distance r. The benefit of using electric potential energy instead of the electric force is that energy is a scalar, and calculations are much simpler. There is no direction, but the sign matters. And notice now, this is no longer the r squared we had for the electric field or the electric force. It's now just r. What is this electric potential energy? It tells you how much energy is stored by work being done on the system and is now available to return that energy in a different form, such as kinetic energy. If two positive charges are placed near each other, they are a system, and they have positive electric potential energy. Once released, they will accelerate away from each other, turning potential energy into kinetic energy. If you have two positive charges near each other, right, the electric field force is trying to push them away, you have a positive potential energy. You put in plus values for both q's and you get a positive number. This means that it takes a force by an external agent, here's your external agent, would have to be pushing this way to keep them from moving farther apart. If you have a positive charge and a negative charge near each other, you have a negative potential energy, right? You put in negative q there, multiply through, and you get a negative k, large Q, small q over r. That means it takes a force by an external agent to keep them from getting closer together, right? They want to go like that. The electric field force is moving the charges towards each other. So if we take an external force, it has to push in that direction to keep them from getting together. If you have two positive charges or two negative charges, there will be a positive potential energy. All right, we already showed this one. You know what? The same thing works here for two negative charges. And here's the math. Potential energy is k times each q. They're both negative. Negatives cancel out, and you get a positive potential energy. This means, once again, that it takes a force by an external agent to keep them from flying apart. To get the total potential energy for multiple charges, you must first find the potential energy due to each pair of charges. Then you can add the energies together. Since energy is a scalar, there is no direction involved, but there is a positive or negative sign associated with each energy pair. For example, if you have three charges, the total potential energy is potential energy between 1 and 2, potential energy between 2 and 3, and then the potential energy between 1 and 3. So I think that's all the combinations. It is. And this is just a notation issue. UXY, that's the subscripts there. That's the potential energy of charges X and Y. Example 1. What is the electric potential energy of two charges of 4.2 microcoulombs and 6.1 microcoulombs, which are separated by a distance of 50 centimeters? List the givens and be careful to convert microcoulombs to coulombs and centimeters to meters. So here's our electric potential energy equation, KQ1Q2 over R. Put in Coulomb's constant, the Q's in terms of coulombs. Here's our distance. Now remember, we don't square the distance this time. And we get a potential energy of 0.46 joules. What is the electric potential energy of two charges of minus 3.6 microcoulombs and 5.2 microcoulombs, which are separated by a distance of 75 centimeters? We start by converting microcoulombs to coulombs for our charge, right? 1 microcoulomb is 10 to the minus 6 coulombs, and converting centimeters to meters. Here's our equation. We substitute in the values of the charges and Coulomb's constant. Be sure you carry the negative sign there, and you get negative 0.23 joules. What does a negative sign mean? It means these charges will get together. They will be attracted to each other. Another name for that is a bound system. Compute the potential energy of a system of three charges, and the charges are listed here with their magnitude, with their sign, and where they are located on the number line. And we'll work through this on the next few slides. We'll start by computing the potential energy between the first two charges, Q1 and Q2. We'll have to change millicoulombs into coulombs, and 1 millicoulomb is 10 to the minus 3 coulombs. Here's our equation. We're given the charges, but what else do we have to find? The distance between them. So that's 1, 2, 3, 4, 5. Or you could have just done 3 minus a minus 2 and gotten 5. Either way works. Put that in the denominator here, and then you get negative 1.29 times 10 to the 5th joules. We've calculated the potential energy between Q1 and Q2. Now we're taking another pair, which is Q1 and Q3. So we have the same equation. We have the charges, and again, just reminding you, convert millicoulombs to coulomb, where 1 millicoulomb is 10 to the minus 3 coulombs. We now need to find the distance between Q3 and Q1. Well, Q3 is at 9, Q1 is at negative 2, so 9 minus a minus 2 is 11. Or you can just count the boxes. But in either case, there you have it. There's your distance. And we have a positive 1.27 times 10 to the 4th joules. So we've computed the potential energy between Q1 and Q2, between Q1 and Q3. What does that leave out? Now we have to do Q2 and Q3, and that's the last pairwise computation. So here's K, Coulomb's constant. Here's Q2. Here's Q3. And then what's the distance between these two charges? Well, you go from 3 to 9. That's 6. That's our distance. Do the calculation. Minus 3.06 times 10 to the 4th joules. Last step. Find the net potential energy of the system by calculating the algebraic sum of each pair of charges, which we've done on the last 3 slides. So that's going to be U12 plus U13 plus U23. Make sure you carry through the negatives where we had them. Here's what we got. Add them together, and we get a potential energy and net potential energy of the 3-charge system of negative 1.47 times 10 to the 5th joules.